Today we're gonna look at the second homework. The deadline is still the same, so it's next Friday. Should be enough to finish both homeworks. I don't think it's gonna be too long, but yeah, let me know if you find difficulties as you try to solve it. But yeah, now we will try to go through this together. So let's see. Please feel free to interrupt me and ask questions if you feel like some concepts are a bit too abstract, or you want to maybe discuss a bit more some of the questions, exercises. Yeah, the structure is similar to the one from last day, right? You have mostly coding questions. You will have like some template, and you will have to fill in basically some lines of code in the block between begin solution and end solution, right? And then when you submit your notebook, we will check that everything runs beginning to the end. So you have to make sure that the code you write inside these blocks is compatible with the template we give you, and then you write passes the test we put. There's inside the notebook there are already a few tests, so you can see if your code is working or not mostly. So that's already can help you be coding up your solutions. I've also included a couple of open-ended questions, so like a bit of mostly questions to see like if you understand a bit the concepts behind the equivariant network, and some questions on just to analyze your results. So in those cases, you will see like a text box with your answer, but you just have to fill in your answer in that specific block. Yeah, that's it for the introduction. So, oh yeah, another point is that we also included a small bonus question. You don't have to solve this question to get all the points. So you can still get full grade without solving this question, but I thought that maybe it's a nice question to add on top. If you find the homework too easy, that can give you a bit more challenge. And then it can also give you a few more additional points that will be counted on top of your grade later. So that could be nice, but you don't have to solve that question, and I'd recommend you trying to solve it only once you have finished the whole homework. So, okay. So I'm not sure how familiar all of you are with the definition of group, and so I tried to, in this notebook, you will see that this notebook is quite verbose. I try to go very, very slowly through each concept, and I define I introduce all those definitions. If you're already very familiar with these concepts, you will find this a bit boring. I hope not too much, because I'm defining everything, but that can be helpful for you if you are still not sure about what exactly is a group and so on. So, okay, this is just a small introduction. I want to just give you an overview of what we're going to do. So the first part of the homework is going to be a few exercises, a few definition about group theory. So we are going to define what is a group. We're going to play a bit with the group. You're going to try to implement a couple of groups to see a bit what are their properties, what they do. And then we're going to try to use these concepts to slowly build a group equivariant neural network. To do this, you will use NumPy and PyTorch, so just standard tools. Yeah, we're going to just slowly build all the building blocks, and then hopefully in the end of the notebook, you will be able to combine them to build a group equivariant neural network. Finally, you will train this neural network on MNIST, on rotated MNIST. We provide you already the training code, so you just have to basically build the model, and you can play then a bit to try to achieve the best results you can. So you can take it a bit as a challenge to where you have to improve the model. Okay, so the first part, is here we are just installing a few useful packages, so that should be fine. And then we immediately go into group theory. Again, please give me some feedback, like how do you guys feel about group theory? Has any of you already, does any of you already know the definition of a group? Have you already seen the definition of a group? Can someone tell me something? Don't be shy.
You may also write in the chat if you're not comfortable speaking.
Yeah, of course. Okay, should I assume that no one is really familiar with the group theory? Okay, I take it as a yes. Then let's try to go through this together slowly. So first of all, we define what is a group. A group is nothing more than a set of elements. Okay, thanks for the answer. So yeah, no worry, we're gonna go through this together. So a group is nothing more than a set of elements, right? So imagine like a set of elements. We give them a name, right? It could be A, B, C, D, right? Together with a binary operation, so which we call group law, which is this dot. Imagine it as a product that given two group elements gives you back a new group element, and this product needs to satisfy a few properties, which we call group axioms. The first one is associativity, which means that if you have a group element A, a group element B, and a group element C, you can either first combine B and C, and then combine the result with A, or first combine A with B, and then combine the result with C. In both cases, you should get the same result. Note that B times C, right? This gives you, like, imagine a new group element which we call D, right? And now we take D and we combine it with A again, and we get a new result which is, I don't know, F. And we want this to be the same on the other side. Then there is always an identity element. So there is a group element which we call E, right? Such that for any other group element, we can multiply our group element with identity, and it will still give us back the same group element. And it doesn't matter in which order we multiply these guys. And finally, there is an inverse. So for each group element, there is another group element which we call G inverse, such that G times G inverse is going to be equal to G inverse times G, which is equal to the identity. So far, like, this looks like these are, you know, quite intuitive properties. Like if you just do basic arithmetic, right, you work with integers, you know, or real numbers, and you try to do the sum or the product, right? Those are pretty much the same properties, right? But let's keep it simple. So imagine that this the group is the group of integers, right? So, and the group law is the sum. So an element of G is an integer, right? You can take two integers, you take the sum, and they give you another integer. And you can sum another element, and that gives you another integer. So for example, let's verify that the integers are a group. Again, G is our set of all the integers. The product is the actual sum of the integers. And now we have that if you have A, B, C, is it true that A plus B plus C is equal to A plus B plus C? But we know that from the integers it's true, right? If we do 1 plus 2 plus 3, right, it's equal to 1 plus 4, that gives us 5. And it's the same as if we do 1 plus 3. No, what did I say? 1. I forgot the numbers. Okay, let's do it again. Let's say we have 1, 2, 3, right? So we can do 1 plus 2 plus 3. So 2 plus 3 gives us 5, plus 1 gives us 6. On the right, we can do 1 plus 2, that gives us 3. And now we sum 3, which gives us 6. So yeah, integers addition, right, is associative. Now we have the identity, right? So there's an identity element such that when we sum a number to this identity element, we always get back the original number. And in the case of integers, this number is 0, right? So if we take 5 plus 0 is the same as 0 plus 5, which is again 5. And this works for every number, right? If we have x plus 0, is always going to be equals to x. And finally, we have an inverse. So for each number, there is another number such that if we do x plus y, so for each number x, there is a number y such that x plus y is equal to 0. And this number is just minus x, right? So if you have x plus minus x, it always gives us 0. So we verify that integers are a group. Integers actually are a special case of group because they have an additional property that we don't have here. So integers are also commutative. So if you do a plus b is always equal to b plus a, right? But this is not a requirement for groups. So these are a special case which are called abelian groups, but it's not a necessary condition. So in general, you cannot assume that a, in this case, a times b is equal to b times a. This is generally not true. So yeah, another example of a group, right, which is the one we will care about more, is the group, for example, of rotations, right? A rotation by theta degrees, right? You can imagine that as a group element. Now you can combine two rotations by alpha degrees and beta degrees, and that is equal to a rotation by alpha plus beta degrees. And for any rotation of alpha degrees, there's an inverse rotation of minus alpha degrees, or if you prefer, 2 pi minus alpha, right? And what's left, oh, and there's also an identity element, of course, which is the rotation by 0 degrees. If you, this again, the planar rotations are still a commutative group, so it's still a special case. But now if you also take not only rotations, but also mirroring, so you have rotations and mirroring around one axis, right? Now this group is a bit more complex and it's not commutative anymore. So if you take a rotation and then you do a mirroring, it's different than first doing a mirroring and then applying a rotation. I don't have a visualization for that, but you could try yourself, like on a pen and paper. You can try to draw an image to a reflection along one axis and then rotate it by 90 degrees, or trying to first rotate it by 90 degrees and then applying a rotation, and then applying a reflection to convince yourself. But still, the group of rotations and reflections is a group, right? So we can test this associative property. There is an identity, which is applying no rotations and no reflections. And there is an inverse. If you apply a rotation and a reflection, you can undo it by rotating it back by the same angle and applying again the reflection. So yeah, these are this is most of what you need to know for groups. You probably will not need much more in this homework. So yeah, let's try to go on. Do you have any questions about groups? Is this is a bit more clear now what a group is?
Yes.
Okay.
But I have a question.
Sure.
Hello?
Yeah, I can hear you.
Okay, sorry. I have a question. So my question was going to be, is there a boundary on the domain of the elements of a group? Like, is a group bounded? Is the domain of a group essentially maybe a set of integers, a set of real numbers, or it could be, you know, a set of some other kind of abstract types or something?
Yeah, good question. So so it's so this is where we talk about abstract group theory. So in general, right, when you think about a group, you have quite a concrete representation in mind. So if for example, before I was talking about integers, right? You have a clear picture in your head of what is an integer, right? You have a set of numbers. Or I was talking about rotations, right? You have a clear picture of what are the rotations, right? So you can imagine like this rotation happening. a group, the elements of a group don't necessarily need to be like anything. Like they can be just letters, right? As here I wrote ABC, right? With an operation. So you can say like G, like as a set, right? Is a set containing objects, whatever they are, right? It doesn't matter. And then you have an operation that tells you, given two objects, let's combine them together to get another object. For example, in the group of rotational reflections, we started, well, first we had only rotations. You can imagine them as numbers, if you want, between 0 and 2 pi to represent a rotation, right? So you could see, okay, my group of rotations is a set of real numbers, right? But then we also added the reflections, and reflections are, I mean, either you do a reflection or you don't. It's not like a real number. You can imagine it as a Boolean variable, right? It's 0 or 1. But yeah, it can be anything. For example, let me make a more complex example. If you imagine the group of rotations in 3D, right? The rotation in 3D is, if you're a bit familiar with the, I don't know, aerodynamics, I think, where do they appear? I don't know, you have like, for example, in an airplane, right, can have like, can be tilted in this way, right, or in this way. You have 3 ways basically to parameterize all these different rotations, but things get a bit more complicated. They're not like just, you cannot represent a 2D rotation by just storing 3 numbers. You have to be a bit careful. Like these are all things that emerge when you want to kind of parameterize a group. So imagine like a group as some kind of space or a set, and numerically, like when you implement them, you want to somehow represent them. So you end up with having like a set or a list, I don't know, of numbers, right? But that's like mostly just a way to index these elements in abstract. Usually, like when you look at a group from a definition, right? You look at it at more abstract level. Like for you, it's a set of I don't know, letters, and each letter is representing something. But you don't really look at what precisely this letter is. So again, for example, the group of of rotations in 3D, it's a very complex set. There's rotations, planar rotations around any possible axis, and it's quite complicated to write down numerically, like what are the elements. But you can still talk about a group. You just say, I have a group G of rotations in 3D, and I say an element of this group is a letter A, right? This letter A will represent something, right, somewhere. But in the meantime, you can still play with the properties of the group. You can still say, if you have 3 rotations in 3D, you can first apply 1 rotation and then the other 2, or first the first 2 and then the last one. You have an identity element, you have an inverse element. So you can still do these things without really looking into what is the group. So yeah, to close the question, in practice, when you implement a group, right, you want to imagine the elements of the group as maybe numbers, but mathematically speaking, they are just a set of whatever. Like you can put anything you want in this set, as long as you have a map that is satisfying these properties. Does it make sense to you?
Yes, it does. Thank you.
Okay, nice. Any other questions on this? Okay, then I go on. So here you have the first exercise. This is just a simple test to see like if you understood these properties. So in this exercise, you need to prove the following statement. Here we have seen that for each group element, there exists a group element which is its inverse. So such that if you do G times G inverse, you get the identity. It turns out that in a group, this inverse element is always unique. So there's a single group element that we call G inverse, such that G times G inverse is equal to the identity. So what you need to do in this exercise is proving that basically, suppose that there's a group element A and a group element B and C, right? What you want to prove is that, what is it? Yeah, you have ABC. You want to prove that if B is an inverse of A, so A times B is equal to identity, but also C is an inverse of A, so A times C is equal to the identity, then it must be that B is equal to C. So indeed, the inverse of A is unique. You can prove this by using basically this property here, right? And the properties here. You just have to combine them, and you can basically show that indeed B is equal to C. And that's the first question. Is this clear for you? I don't want to give you too many hints on how to solve this problem. If you find yourself a bit stuck here, we can discuss it a bit more in detail, but I would like you to at least first try yourself to solve it. Is the question clear for everyone? Okay, nice. Then we pass now to the second exercise. So now we look at a bit more practical example. So we introduce our first group. This is the group of 90 degrees rotation. So we call it the cyclic group of order 4. Order means like of sides 4. And the reason why it's because the 90 degrees multiples of 90 degrees rotations are only 4. You can either not do any rotation, you can rotate by 90 degrees, by 180 degrees, or 270 degrees. If you rotate one more, right, you just go back to a rotation of 2 pi, right? So it's like not rotating at all. And the nice thing about this group, right, is that we can parameterize it. We can index its elements, right, by simple with an integer, right, which with values 0, 1, 2, and 3, right? That tells you like the multiple of 90 degrees in practice. So an element will always be a rotation by r times pi alpha, r times 90 degrees. So again, to reconnect to your previous questions, right? How you should imagine an element of this group. You can imagine it as you want. You can imagine it as an actual rotation by 90 degrees. You can imagine it as an angle between 0 and 2 pi, so which are precisely 0, pi half, pi, and 3 times pi half, right? So as 4 real numbers. Or you can also imagine it as just the 4 integers, right? These 4 integers. Those are just valid ways to imagine this group. And if you're a bit familiar with discrete algebra and discrete mathematics, you will recognize that this group is equal to the group of integers modulo 4, which usually is written like this. So indeed, if you take now 2 rotations, right, by let's say r and s multiples of pi, and you combine them, what you have is a rotation by r plus s modulo 4 times pi half. Does everyone know what I mean by modulo 4? Yeah, so modulo 4 is what you have in Python with the percentage symbol, right? It gives you basically the reminder. So let me see. So if you have like 3, 6, 7 modulo 3, right? This is going to give you, it's going to take a while to run. Yes, yeah, it's 1. So this is basically telling you that 3, the closest multiple of 3 to 7 is 6. Then you have 7 minus 6, which gives you 1, right? So that's the reminder. In our case, right, suppose that you have r is equal to 2, s is equal to 3, right? Now we have r plus s, s modulo 4, right? That's 1 again. So that's basically making sure that if you sum r and s, right, and if you go beyond 4, rather than going to 5, 6, 7, you just go back to the start from 0. And that's the same idea as rotations, right? If you do a rotation by 90 degrees, you go up. If you do another one, you go here. If you do another one, you go down. Now, if you're at 3 times pi half, right? If you do one more rotation, you don't go to 4 times pi half, but you go back to 0. that's why we have this modulo operation. Is that making sense to you? If I don't get any questions or answer, I assume yes. Okay, nice. Okay, so basically in this exercise, you will just implement this group. So in Python, so we build a class for the group C4. This is going to be a static class, so you don't need to instantiate it. It's just a way to store the two operations close to each other. So you will implement basically these two static methods, the product and the inverse, which should in turn implement, basically the operation that given G gives you back G inverse, and the binary operation that given two group elements, it returns to the third group element. In practice, the operation of multiplication you have to implement is this one. So R times S, right, gives you R plus S modulo 4. We're going to implement, we're going to store the group elements with these integers, right? So we're not going to store them as floating points numbers, which are multiple of pi alpha, but we are just going to use 0, 1, 2, 3. For the second part, instead you will need to implement the inverse. For the inverse, I did not give you here the solution of what is the inverse of R. So you have to figure out yourself what is the inverse of the group element R. But you can do it yourself using these solutions, right? So you know that, well, you saw here, right, how to show that the inverse is unique. You've seen these properties. You know actually what is the definition of this product. So now you can kind of invert this operation. If you know that there should be a G inverse such that G times G inverse is equal to the identity, you can now write this down and invert this equation to find out what is G inverse. And that's what I want you to write here. Is that clear? Okay. Yeah, so once you have implemented these two methods, we're going to check that your implementation is correct. So to do that, we try a few combinations and check if the result is you obtained is the right one. So again, if you multiply 1 by 3, right, it's a rotation by 3 times pi alpha plus rotation by pi alpha. That should give you a rotation by 0. If you multiply, if you combine a rotation by 0 with a rotation by 0, it gives you back a rotation by 0. 2 and 3, if you do a rotation by pi, and then a rotation by 3 times pi alpha, you go back 1, 2, 3, you go back to a rotation by 90 degrees. And then we check that the inverse of a rotation by 0, right, is a rotation by 0. And a rotation, the inverse of a rotation by 90 degrees is a rotation by 3 times 90 degrees. Because you see that's what means to reach the identity. So if you rotate by 90 degrees, you miss 1, 2, 3 more rotations to go back to the identity. Okay, so that's the first coding exercise. The second one is a bit more complicated. We're going to do precisely the same. This time we're not going to implement the group of 4 rotations, but we're going to implement the group of 4 rotations and reflections. So you can imagine this group as as containing these 8 elements. So as before, we have rotations by 0, pi alpha, pi, and 3 times pi alpha. That's the same as before. But now we have 4 more elements. We have a reflection, F. You imagine that F is a mirroring operation along this red line. So if you have like an image, you do a mirroring with respect to this image, this line. And then the other 3 elements are going to be first applying a reflection and then applying some rotation. And you can actually check yourself, and I invite you to try by hand, that if you do a reflection always along the horizontal axis, and then you apply 1 rotation, so either pi alpha, pi, or 3 times pi alpha, you're just going to obtain something that looks like a reflection along these other 3 axes. So we can try an example. suppose that you want to do this. You apply a reflection and then you rotate by pi. So this is equal to first applying this reflection and then doing this rotation. And what you can find is that this is going to be equal to a reflection along the vertical axis. I could have put an image to do that. Let me see if I can try with showing you something. So you can imagine like this mug, right? I don't know if you can see it well. You can now apply a reflection to this mug, right? Around the horizontal axis. It's gonna go upside down, right? And now you apply a rotation by 180 degrees and it goes like this. And this is equal to having done like a reflection around the vertical axis in the first moment, right? So again, we start with a mug like this. We want to obtain a rotation, a flip of with respect to the vertical axis, which goes like this, right? But this is the same as first applying a mirroring with respect to the horizontal axis, right? And then rotating this by 180 degrees, which goes back like this. This is the same as doing a mirroring with respect to the vertical axis. So yeah, this is just to show you like what are these elements. In general, that means that an element of the dihedral group, we call this group dihedral group, can be parameterized as a pair of numbers. The first number, R, is 0, 1, 2, 3. It's like before, it represents a rotation. While the second number, F, is either 0 or 1, and it tells us whether we first apply mirroring or not. That's mostly, yeah, that's all about this group. What you now need to know is only how do we combine reflections and rotations. But you can try yourself, like imagine like an object, try to do reflections and rotations as I did now to see how they combine. But here's the shortcut. You know that if you take 2 reflections, you get back the identity. So if I my mug, I apply a reflection, and now I apply it again, I get back the same mug, right? It didn't change. Second, if you have a reflection followed by a rotation, is the same as a rotation followed by a reflection is the same as first doing the reflection and then doing the opposite rotation. So if we do again our mug, we can either first rotate our mug by say 90 degrees and then applying our reflection, or we can do a rotation by minus 90 degrees, which was this, and then applying our reflection. No, I did it the wrong way, sorry. It was first reflection and then the mug and then the rotation. So again, we can first apply our rotations by 90 degrees and the mug goes down, right? And then our reflection with respect to the horizontal axis and the mug goes like this. Or first we apply our reflection and then our rotation by 90 degrees. The mug turns like this. You can try that yourself with maybe a piece of paper to convince you that this is what's happening. So now you know how to combine the group elements of this group. Well, actually, you know how to combine a couple of them, but you also know how to combine 2 rotations from the previous exercise. And what you need to do now in this exercise is finding out all the possible combinations. So again, you know how to multiply 2 reflections. You know how to multiply a reflection with a rotation. You know how to combine 2 rotations. Now what you need to find out is how to combine a rotation and a reflections with a rotation and a reflection, all possible combinations. This is what you should then implement in this class. Again, you have this static class with the 2 methods, the product and the inverse. Also, yeah, you have to find out yourself how to compute the inverse of an element of the dihedral group. So what is, for example, the inverse? Well, you already know what is the inverse from the previous exercise of a rotation. What you need to find out is what is the inverse of, for example, a reflection followed by a rotation by pi. You can do that yourself, like try to write down rotation times f, put the inverse, and then try to manually solve the equation. One property could be useful to you. I forgot to mention, but you can derive it also yourself. Let me add it here. In general, if you have a so this is a property you may need to solve these exercises, or at least to solve them faster. If you have the inverse of missing a dot here. If you have the inverse of A times B, is equal to first inverting A and then inverting B and taking the product. Not that you have to swap their order. It's a bit like with matrices, right? If you have the inverse of a matrix A times a matrix B, right? And both A and B are invertible, you can just take the inverse of each of them independently. So I think that you've already seen something like that, right? Yeah.
Yes, please. In the where you do the composition of the rotation and the reflection, why in the right side you did not put the binary operation down?
Where is it? Oh yeah, that's just a typo. I mean, in general, right, I'm putting this dot everywhere to make it a bit explicit, but it's common also to just skip it, right? If it's clear that both of these elements belong to the same group, right? You can also just not put the dot, right? It's like in arithmetic, right? Usually you write the multiplication with a cross, right? But after a while you start removing the cross because it's clear that if you put two variables close to each other, right, you're going to take a product. So it's the same, but let's make it very clear. So I will put the dot as well here.
Okay, so I want also to clarify something. So in that in that composition of operation, you start with the second one, right? I mean, you start with the second one. Like if you have a rotation, and if you have the reflection and rotation, you start with the rotation before doing the reflection.
Yeah. So imagine that when you apply, I don't know, one of these guys, right, to an object, you start. It's like a composition of functions, right? So if you have f, it's like saying f of g of x, right? So first you apply g of x, and then you apply f on the result. Let me write this to have a. So I don't know. It's if you have like two functions, you say like f of g of x, right? So if you had to write this, right, you first you take x, you first compute g of x, and then the result you apply f. So that is pretty much the same concept. And yeah, or imagine that when you have like a c, right? If you want to compute something, right, here, you first you have to group them, right? So you first do this. So first you compute these guys, right? And then on top you apply a. This is also equal to do this, right? That's also fine. You can always do that. But the order of operations, right? You are not combining A with C. You first combine B with C, right? You have to combine elements which are close to each other. So again, the point is that what you see here, right? It's just something like that. You have, I don't know, for example, my mug, but in this case, I was showing the rotation of a mug, but you can have like another object here, right? And you want to multiply it by some group element, which is itself the multiplication of two of them. To do that, you can, well, the idea is that you can first compute this, right? And then on top, once you're done, you apply A. So for example, in this case, you first apply your rotation and then you apply your reflection.
Okay.
Does it make sense?
Yeah, yes, it makes sense. So I have another question about the reflection. So
Yeah.
how do you set the plan of reflection? So because I don't know.
Oh yeah, in that case,
you do not give I don't think that you give any information about that one. So if I have an object, so where do you set the plan of reflection?
That's up to you. So in general, right, what I said is that let's say take F, right, and let's say the reflection is along this axis, right? I said the reflection is the horizontal one. Now, if you say that F is the horizontal one, you will have that the other three are going to be these three. But you could say from the very beginning, I actually want the reflection to be, I don't know, a diagonal one, or like a line, but with 5 degrees rather than 0 degrees, right? And that's totally fine. It's not going to change. So the interesting part is that it doesn't matter which reflection axis you take here, because the group is going to be still the same. So basically, the equations here, right? The definition of the group elements, it's going to be the same regardless of where the reflection F happens. It's going to make a difference when you take, of course, an image and you do the reflection, because you said, for me, a reflection is along this axis. So when you implement it as a transformation of your image, then that is going to make a difference. But when you look at the group as just a set of elements, and now these group elements combine, in that case, the reflection axis doesn't matter. For simplicity, what I'm saying here is that F is a reflection along the horizontal axis, right? So you can, for simplicity, just assume that F is a reflection along the horizontal axis. But in practice, it doesn't really matter. You don't need to know this. Is this making sense for you?
Yeah, I think that is clear now. Thank you.
Yeah, sure. Delete some parts. Okay, so yeah, basically here you can have to play a bit with these definitions to find out the right operation to implement here and here. And again, now we check if your implementation is giving the right results. So what we do is we implemented the identity element. The identity element is no reflection and no rotation. The reflection F, right, contains only a reflection but no rotations. And the rotation by 90 degrees is no reflection and 1 rotation. And now we check if these operations you implemented satisfy our our instructions. So we said that we should have these properties, right? So we check, well, first of all, that the identity times the identity give us the identity, that a reflection times a reflection give us the identity, because we know that the reflection is the inverse of itself. Then we check that our reflections times a rotation is equal to the inverse of the rotation times the reflection, right? And then we check a few random combinations. We check that the group axioms are satisfied. So you have that a random object, right, a random element times the identity is still giving us the same object. The same holds in the other direction. And then we try that B times the inverse of B give us the identity, but also the inverse of B times B give us the identity. Now we check the associative properties. So A times B, the result times C is equal to A times B times C. So yeah, this is just to check that your implementation is working. You can yourself change these values, right, to see if your implementation works also with the other combination of numbers. You're advised to do that, so you can check if actually your implementation works. But yeah, this is all about this exercise. Okay, we can now pass at the second part. So now we introduce a second definition, and it's the definition of a group action. It's nothing really fancy. In practice, you've already seen what is a group action. in a group action, you have like a group G, and now you have a G space X. X is just a set of objects, and now you have a new map that gives us from a group element and an object. It gives us the object transformed with that group element. So again, imagine that your set X is the set of all possible mags, and G is the set of rotations and reflections. So now what I was showing you before actually was a group action. So the mag in this position is an element of the set X. The mag in this position is another element of the set X. And now you take a rotation by 180 degrees. So G is a rotation by 180 degrees. This rotation is taking this object and it's mapping it to this object. Again, both this mag and this mag are element X of our set X, right? So, for example, this small X is the mag in this. Is the mag in this position. This element G is a rotation by 180 degrees, and G times X is going to be this. This is X. This is G times X. And note that as G times X is belonging to the set of all mags, all the possible mags. So yeah, this operation is to satisfy a couple more properties, which are just required to be consistent with the operations of a group. So there must be an identity, right? So if you take our mag and you multiply it by the identity, it must stay like the mag. So the identity should not be changing the mag, which is quite reasonable, right? That's like in our intuition. And then, yeah, you have to be compatible with the group action. So if you first rotate the mag by 90 degrees and then rotate it, if you first rotate the mag by 90 degrees and then you rotate it by 90 more degrees, it's the same as rotating it by 180 degrees in the first place. That's all. So it's just to basically be able to play with the group law right here, or with the group action here, and the two things should be compatible. Right? You can first group together all the group elements, or or apply each of them independently on the object one after the other. So yeah, an example of group action is that of our group C4, right? On images, right? So we have an image and the group is rotating it by 90 degrees. So let's say that X is the set of all 33 by 33 grayscale images, right? And G is our group of 90 degrees rotations. What we have is that, well, okay, first of all, I don't know if you're familiar with this view, but you can imagine like a grayscale image, right? As a function that gives us for each pixel, right? The coordinates of the pixel. It gives us the color of that pixel. So basically, we interpret an image X as a function that goes from a pixel location, right, to the color of that pixel location, which belongs to R, because it's a real number. Sorry. And so how do we define precisely a rotation of an image by a group element? We say that, okay, well, first of all, the rotation, we consider them as counterclockwise, so a rotation by 90 degrees. I don't know if you see me mirror, so maybe if I do this for you, clockwise, I'm not sure. But yeah, okay. A rotation is counterclockwise for us in this case. And you define it as a rotation of an image X is going to give you back a new image, G times X. And the value of the new image at pixel P is going to be equal to the image X before, evaluated not at pixel P, but at G inverse times P. So if G is a rotation by 90 degrees, the rotated image at pixel P is going to be equal to the previous image, not at pixel P, but at the pixel that was mapped to pixel P. Just need to go back in the previous image and to check where the pixel is coming from in practice. So So yeah, I don't know why this is an error, but it should be running. What you need to, well, in this exercise, you don't need to do anything. I'm just providing you this function. What we are doing here is just implementing this action. So given an image X as a PyTorch tensor and a rotation R, we want to return the rotated image. Nothing fancy, it's just PyTorch does it already for you. So you just have to do a rotation 90 of X R times. That's it. We specify the dimensions -2 and -1 because well, we want to use this function later in a neural network. And you know that usually in a neural network, right, you have the last 2 dimensions are the image dimensions, then you have the channel dimensions and the batch dimension. So you have 4 dimensions, right? So in this way, we rotate the last 2 and we can use this function also for mini batches, which is convenient. But yeah, you can then verify yourself. Okay, I don't want to run this notebook because otherwise I will have to, you will have it already kind of not clean. I see. Okay, yeah, I mean, you can now generate like a random image and try to see that yourself that this function rotates the 2 images. Again, nothing fancy here. We are just taking an image and rotating it by 90 degrees. It's just that we are building some framework to talk about these operations in a more mathematical way. Again, nothing that you need to do here. What we're gonna do now is instead gonna build our first equivariant layer. So, okay. I don't know if you were all attending the talks in the presentation yesterday, but what we did was defining what is equivariance. Equivariance is a property of a function. So we say that a function is equivariant. Let's say that a function psi maps an input space x to an output space y. We say that the function is equivariant if it commutes with the transformation in the input and in the output. What you consider as a function psi in this case is going to be a convolution, like in a normal convolution neural network. For simplicity, we use a 3x3 filter. Let's say that we take just a simple input 1 channel, output 1 channel. We just generate a random filter, and we're going to see this filter later. And now we try to do convolution with this filter on x, our input, right? And gx, computed it before. It's just a rotated image. And now we want to see that we would like the output of these 2 convolutions to be rotated versions of each other, right? So we can now take the output of 1, rotate it back, and get the output of the, okay, I think it's necessary if I actually run this code. I will clean the outputs later, so you don't have to get the dirty version of it. Run this. Okay. Okay, here we see nothing fancy. We just have an image and we rotate the image. You see the 3 dots right moved here. That's all fine. What we do now is saying, okay, we generate a random filter, this filter. We do convolution of with this filter over our image x, that's phi of x, and then we rotate it by 90 degrees. In the other image here, we do first rotate the image x by 90 degrees, and then we apply convolution. If the convolution was an equivariant operation, we would expect these 2 outputs to be the same. They look a bit similar, but they are not the same. You see, like, I don't know, for example, here you have 2 yellow pixels, where you have only 1. The images are not really the same. So what does this tell us? It just tells us that a normal convolutional layer is not rotation equivariant a priori necessarily. So how do we solve this problem? What is the reason why this is happening? The reason is that when you have like a 3x3 patch, right, rotating under your filter, well, the output, right, will depend on whether you put your filter like over your patch or you rotate your patch. So, I mean, of course, this is your filter, this is a patch. The output given at this, when you align them like this, is going to be something. If you do this, the filter is going to give you a different response. And just the response of the filter depends on the orientation of the original image or of the filter equivariantly. So a simple solution is making sure that the output of the filter does not depend on the rotation of the image. To do that, what you can do is to make sure that your filter is an isotropic filter. So it has this shape. This is still a 3x3 filter, but all the values on the ring outside are constant. That means that now if you take this filter and you rotate it, or equivalently you rotate the image under the filter, the response is always going to be the same. Indeed, we can now try to take this 3x3 filter, right? We generated it by setting the central pixel to a random number and the other pixels around to another random number. We do convolution with it, then we rotate our input, we rotate our output, and we plot them. And now, finally, it looks like the two images are the same. So because this filter is a rotation invariant, the output of phi of x rotated by g is the same as rotating x and then applying phi, so the convolution. That's quite nice. We just built a rotation equivariant convolution. So what you're going to do in the next exercise is using this concept and put it inside an actual PyTorch module. What you need to do is building your isotropic conv2D, which has as a parameter number of input channels and output channels. Because what we have shown before was a simple case for a single input channel and a single output channels, right? What you're going to do here is just making sure that you have multiple input channels and multiple output channels. You need to, we are going to always use kernel size 3, stride 1, padding 1, duration 1 for simplicity. But yeah, what you're going to do in the init here is just initializing your set of learnable parameters. Recall that an isotropic filter has only two learnable parameters, one for the center, one for the ring outside. So you just need to store basically two learnable parameters for each pair of input and output channels. And that's what you are going to do here. Don't forget to wrap your tensor of parameters inside a torch.nm parameter and set requires grad equals true, because you want to learn those parameters later. And then what we are going to do is still a normal conv2D, right? So but to do conv2D, you need to actually build your 3x3 filter. You cannot pass just your set of learnable weights. So to do that, you need to implement another function, build filter, which takes your set of parameters, of learnable parameters, and builds these output channels times in channels times 3 filter. So it's gonna do something like what I did here, right? It's gonna build a 3x3 filter, which is empty, right? And then it's gonna set the value at the central pixel, and then the value at the pixels around it. And in the end, you're left with an actual 3x3 filter. So this is what this method should do, and then return. So we can now use this expanded filter, right, to do our normal conv2D. So yeah, your task is basically building this part and initializing your weights. And once you have implemented it, we are going to check that your layer is actually equivariant. So we're going to feed some random inputs. We are going to rotate them and check if the outputs are going to be the same. That's pretty much the idea here. I'm also going to check that you have enough learnable parameters. So that's a good check for you. Again, you should have like for each input and output channel, you have like two learnable parameters, because your filter has only one value in the center and one value around it. So as you can imagine, like, these filters are not really powerful, because they are quite limited. Rather than having 9 learnable parameters, you have only two. You can only learn a subset of all possible filters. So we will see later that this is a problem, but you can already imagine that we generally don't want this. We want to use a bit more powerful filters. To do this, we need to rely on the concept of group convolution. So we actually go a bit more in detail deep in the group theory. The concept of a group convolution, we have seen that yesterday in the labs, in the seminar. I think also probably have seen it in the lessons, but we're gonna go through that in this notebook again. Before that, I want to introduce you another group, which is the group of not only rotations, but of rotations and translations. We call this group the P4 group, or the wallpaper group, which indeed is like a group of translations of your grid and rotations by multiples of 90 degrees. An element of this group, as you can imagine, is parameterized by how much you're translating in the horizontal direction, how much you're translating in the vertical direction, and how many rotations you apply. So in general, you can write like 3 numbers to keep the notation a bit simpler. I will just use the translations. I represent them with a vector of 2 elements. I call it T, right? So this is the translation. It's going to be a 2-dimensional vector telling you the translation in the plane. And now the question is, how does this group work? So first of all, it's easy to see how this group acts on a point on the plane. An element containing a translation and a rotation acts on a point P in the plane by first rotating the point with the rotation and then translating it with the translation. So P, right, transformed with the TR is gonna become first a rotation of P by R, and then you sum the translation. Is this making sense for you? It's normally like a normal notion of a translation in a plane, right? If you have like a point, just translate it by moving its coordinates along a direction T, right? T is like a vector that tells you your translation, and R is like just again a rotation of your grid, so a rotation of your points in the plane. You just need to choose which of the 2 operations to do first, and like we just choose these just to standardize everything. We say first we apply rotations and then we apply translations. Is it clear for you? Okay, nice. So now you know how this group acts on the space of points on the plane. What we have not said is how the group elements combine with each other. So if you have now a translation by T and a rotation by R, and another element which is a translation by P and a rotation by S, you can combine them with this rule. So basically rotations combine with each other. Just R times S gives you R times S, while the first group element, T and R, act on the translation P here as if it was a point in the plane. So we just get first a rotation of the point P, and then you translate it by T. You can actually derive this yourself, like by trying to say, like, I have a point on the plane, I first apply on it this guy, and then I apply on the result this guy, and you will see that mathematically, right, if you use this equation, you're gonna start to simplify and combine elements until you get this result. So again, for all of these properties that I'm defining, I invite you to just try it yourself, right? It's a couple of algebraic steps, and you can see a bit more clearly what these equations mean. And here I actually give you also the inverse. So if you have like a translation and a rotation, the inverse is the inverse rotation. And yeah, this is not super nicely written, but what this means is a translation by minus translation before, right? But also rotated back by the same amount. So what this means is take t as a point, right, in the plane. Now you take minus t, which is the inverse of t, the translation in the opposite direction. And now this result, you rotate it back with your inverse rotation. So the result of this is still like two numbers. It's like a translation in the plane. So yeah, that's it. Again, try to verify this yourself. You can try to put the inverse and manually solve these elements. Like as I said, like these acts, you can imagine this element as acting first with a rotation, then with a translation. So if you invert it, it's like the property before, like the inverse of A times B is equal to the inverse of B times the inverse of A, and then you can basically find this equation. Okay, now we can go to group convolution. We talk about group convolution. I need to always say that in practice these are cross correlations, but we keep using the nomenclature from deep learning where we use convolution to talk about correlation. Okay, the definition of a group convolution in general is that you have a function, your image x, right, over all the points in the plane. So you see P is in the plane, x of P, and then you have your filter psi, which is also a function, is in x, like x is the space of all planar images, right? And so also psi is our filter. Usually in a convolution, what you do is taking your filter and try to apply all possible translations and you move it around on the image. Here on the group convolution, we actually do not only translations, but also rotations. So like the output of our convolution is going to be a number for each possible transformation, translation and rotation, TR, that we apply to our filter. And yeah, then it's basically just this equation. You see that you sum over, integrate over all the image, and you have your image x evaluated on each point, and your filter instead is transformed by shifting it by some translation, but this time also applying some rotation. A normal convolution neural network would just not have this R inverse. So you would remove this part and then it's a normal group convolution. What you should pay attention to now is that, however, that the output is not anymore only a function of t, which was a point in the plane, but it's also a function of r, the rotation we applied to our filter. So that means that the output of our group convolution is not anymore an image, but it's a function over, again, all possible translations and rotations. So we call this space now Y. So it's the space of all functions over the elements of the group P4, the group of translations and the rotations. Note that the group P4, so our group G in this case, has a natural action over these functions as well. So if you have Y, which is a function over right, T and R, we can, or in this case PS, right, we can transform Y by just, I mean, just like before when we had an image, the rotated image we evaluated on a point, and that should be equal to the original image evaluated on the point rotated back. That's the same here. So our function transformed evaluated on a point PS is equal to the original function evaluated on PS, but rotated back with the inverse of the transformation here. And here I just applied the formula, the equations we had before to simplify. The main concept here is that our group convolution, again, does not map an image to an image, but maps an image to a function over the whole group. This is why we call this operation actually a lifting convolution, because it maps to a space in output which is bigger than the one in input. But the nice part about this is that you can still implement this as a normal convolution, because as I said before, if you fix R, right, so you pick up a specific value of R, this looks like exactly your normal convolution, just with a filter psi rotated by R. Yeah, sure. the lifting convolution, like what we have seen so far, is a lifting convolution because in a normal convolution or a network, you have a filter, you apply it everywhere. For each translation of the filter, you have a number, and the result still looks like an image. So you have like, for each pixel of the image, you put a filter there, and you get a number. So you do it next pixel, you put a filter there, you get a number, and in the end, like you have something that looks like an image. In our case, we have a lifting convolution because for each pixel, you don't get a number, but you get 4 numbers since you put your filter in all the 4 possible rotations. So you see that, I don't know, if before you had a 33 by 33 image and you apply normal convolution, you get in output again a 33 by 33 image. With the group convolution, instead, you get a 33 by 33 image by 4 outputs. So it's like having basically convolution with 4 filters and maps 1 channel to 4 channels. That's why there's a notion of lifting. Like imagine like the number of channels like growing up. That's the concept. Does it make sense for you? You should see that basically this equation is literally like a normal convolution, but then you have you do it 4 times, 1 for each value of r, and each time you do it with a filter which is rotated by r in practice. So this is the concept. The question in why, you mean this one? Oh, this is just telling you now that the output of our convolution is not anymore an image, right? So we also, if we want to transform this output, we don't transform it like an image by just rotating the pixel, but we also need to rotate basically the channels. So if you now hide this S, right, you pretend it's not there, then it looks like you're just rotating the first argument, which is the pixel, the coordinate of the pixel. But our function is now also a function over S, right? So you see that basically you have S in the second coordinate, and you also have to change these. That's what we are gonna actually implement in the next exercise. So let's try to go a bit. Oh yeah, of course. I actually don't know how long, how much time we have for today's lesson, but of course, I'm fine. We can take 5 minutes break. I don't know, Kobe, do you know how much time we have in total here?
Yes, we are supposed to end in about 45 minutes.
Mm-hmm.
Yeah, so no.
I'm fine with taking.
Yeah,
okay.
sure.
I'm fine with taking a break. Yeah. How do you usually do that? 5 minutes. What would you want to do?
Yeah, we could do 5 minutes. But
okay.
before that, someone has a question from the classroom.
Of course.
Okay, please, I have a question about the rotation operation, because I noticed that concerning the rotation, you did not talk about the center of rotation. So in all what we have done so far, so how do you get the center of rotation? Yes. I don't know if you can comment.
That's a very good question. We will see that is popping up in a couple of steps, but usually what we do is assuming the rotation is around the center, the origin of the axis. You really can do it also with respect to any other point. So you can say the rotation is around another point. It's just gonna make all the equations a bit more complicated, but it's totally equivalent because a rotation around another center is the same as first translating back. So you go back to the center, you apply a rotation there, and then you move again with the translation back where you are. So in practice, like a rotation r is gonna by around another center is gonna be equal to tr, where t is some other translation, right? You have to spend a few minutes to try to find out what is the right translation you need to use, but it's the same. So that's it. Like what you can actually see it maybe this way. Let's see. So if you want to rotate by R around the point P, what you can do is say like you want to, and you want to transform a point Q, right? And now you want to translate, you want to rotate it, but around the center P. So what you're gonna do is to first subtract P. Now you rotate it by your rotation. And now you sum again your point. Oh, what did I do? P. So what we do is, if you want to rotate around P, right, you take your point Q, you subtract P, rotate around the center, and then sum back P. But this is going to be equal to actually just rotating Q, right? And then you sum this. So basically, you see that this still looks like somewhat like we had earlier, right? It looks like some translation plus a rotation. So you see that the two things, like just call this guy where T is actually equal to this object. So it's just a matter of applying some change of variables, doing some algebra, but it's still possible. But of course, like writing this down every time becomes a bit more complicated. So you just say, I just say that my rotations are around the center, and that's it.
Okay, thank you. So can we, for instance, can we take a center of rotation out of our domain omega? Is it possible to take? So
one point is that note that my translations, where is defined, is not, and my points are not on a grid of, actually are not 33 by 30 grid, but they are really any point on the plane. Because to make sure that the translation is a group, like you should be able to keep doing translations. So you can start from the origin, now move a bit on the right, and now move a bit on the right, and now move a bit on the right. You cannot say at some point, I cannot go further. You have to go to the infinity. So in general, what you do is assuming that your image is also, you can say, I shift it a bit on the right, then I shift it a bit on the right, and you keep doing that. And you should be able to do that forever. So of course, like your images then in practice are only non-zero on a small subset of the whole plane, right? So in general, this is not a problem, but this is just to say that this already includes what you said, right? A point outside your image is still a point in the group. It's still like a translation you can do. So you can definitely say that.
Okay, thank you.
Yeah.
I think we can go for the break now and come back. Say 5 minutes.
Yeah, yeah. So yeah, I will just switch off my video. I'm gonna take some water as well, and just yeah, make some noise when you're when the break is finished, I think.
All right, sure, yeah.
Okay, thanks. You still see my screen? Okay, cool. So yeah, where we were left. Okay, we were talking about this function y, and this function y now is a function over all the pixels, but also for each pixel is a function over the 4 channels. So like, I mean, imagine it as a, you know, 33 by 33 by 4 tensor. And what we want to say is that the transformation now, like a translation is just gonna translate our tensor. You see that if you set R to the identity, right? So you only have T. What you have is that S is staying S, R is the identity, R is the identity, it's not there anymore. You only have a translation. So a translation is just going to translate your tensor. But if you have a rotation instead, so imagine T is 0 now, a rotation is going to, yes, rotate your pixel, right? That's what it happens here. So as a 33 by 33 by 4 tensor, you just rotate your image. But also, this R is changing the pixels in the 4 channels. So if you have R, for example, equals 1, so it's rotation by 90 degrees, and S is like one of the 4 channels, R to minus 1 is going to move it down of 1 channel. So a rotation of your now 33 by 33 by 4 tensor is going to rotate your tensor as a normal image, but then also cyclically permute the 4 channels. Let's see, sorry, messages in the chat. Yeah, the point is that they're asking why in this equation the rotation is applied on P, and that's the translation is applied on P, but on S we only apply R. And yeah, and the point is that the definition of that we had above here, right? Remember when we defined the multiplication by 2 group elements, right? Was like this. The rotation is only multiplied with the rotation itself, but the translation, right, is combined also with the rotation. And the reason is, I mean, you can imagine, like, you cannot translate a rotation. A rotation is like an angle, but you can rotate a translation, right? A translation is a point in the brain, you can rotate it. So that's kind of the intuition of what's going on there. So yeah, I mean, this equation here, you can, it's just this, right? You can derive it yourself. Like what I did was only taking this product, right? That's an inverse and that's a product. And I just applied this rule, right? And this rule. So you can also verify it. I forgot here the dot. Let me put the dot so it's a bit clear what this means. Yeah. So again, we're gonna see a bit more in practice what this transformation means, but this time you are gonna implement it yourself. So in this exercise, you actually need to implement the transformation I just said. You don't need to apply transformations, translations, but only rotations. So if you now rotate by a R, a function Y like the one we've seen before, what happens is that you rotate the points, the pixels, right, by R, like we had before, but you're also cyclically shifting the 4 channels. Okay, this is what you should implement now in this exercise. You are getting input at a torch tensor Y and a rotation as an integer. You assume that the last 2 dimensions, so dimensions -2 and -1, are going to be the pixels locations, right? So here you can use actually the rotation that we implemented before to rotate it. But then you assume that the third last dimension, so -3, has shape 4 and contains like the 4 channels. What you need to implement in this function then is also this cyclic shift of the 4 channels. I cannot show you the visual result because this function is, you need to implement it. But then what we are going to do now is to take a random image, also with the 4 channels, and we're going to just rotate it using your function. This code already plots the 2 images, so you can compare whether what you built is right, or you can visually see if what you built is right. And then we're going to check if your function satisfies the properties. So we're going to check basically if it's actually true that your rotated image evaluated at PS is equal to the original image evaluated at R inverse P and R inverse S. So here is you see here we actually have to take into account the center of rotation, as someone was asking before, because in an actual image, right, the center of rotation is not the coordinate 0, 0, because that's the coordinate on the top left corner, but it's going to be, I don't know, the coordinate 16, 16, if your image is 33 dimensional. So I'm taking care of that, so you don't have to really delve into this complicated equations, but feel free to have a look. Like, these are tests I'm implementing to check if your code is good. Okay, so hopefully at this point you have understood a bit how these what the features of these functions look like and how they transform. And now we are ready to implement the lifting convolution. Again, remember, the lifting convolution is taking an image, applying a filter in every possible translation and rotation to output not anymore an image, but 4 images, right? So for an image with 4 channels. We want you to implement it in a PyTorch module. So as before, as we did earlier with the isotropic convolution, we're going to have a number of input channels, a number of output channels. I want to just repeat again this example with for the lifting convolution that I think can be helpful. Like in this simple example, like you have an image, that's the image of this lizard, right? And now you do convolution with this filter. That is going to give you like this output image, right? But now we don't do convolution only with this filter, but we do convolution also with these 3 rotated copies of this filter, which means that we're going to have not 1 input output image, but 4 output images. Now, the reason why we do that is that if we now rotate our input images, so suppose that before you had this light color lizard, now you rotate it. So the light color lizard would give us in output these 4 images. You see that the lizard here is vertical. But now if we rotate our image and we do still convolution with these 4 filters, what we're going to obtain is a rotated version of the output we had before. So you see that now the lizard is going to be horizontal. So here it was vertical, right? Now it's horizontal. We rotated the images, but also the output that before was associated with this filter, the horizontal one, is now going to be associated with the vertical filter. So you see that this output now is not anymore in the channel 0, but it's going to be in channel 1. The output that before was in channel 1 is now in channel 2. The one in channel 2 is going to be in channel 3, and the one that was in channel 3 is now going to be in channel 0. This is the cyclic permutation of the channels. I think that maybe like looking at it with an image is a bit more intuitive than like reading the equation before. So yeah, I would recommend you to look at a lot at this image until you understand exactly what's going on here. You think about what happens if you rotate the input. Look, for example, at this particular filter here, right? If the output at this particular pixel was obtained by putting this filter in this position, right? But now if you rotate the image, the same output will be obtained by the rotated filter, right? Because now it's going to be here and it has to be vertical. So the output will be now found in this position. So it's rotating the image, but also like now associated with a different filter. Okay, so what you need to do is again, just fill in this template. A filter now is parameterized by all your values. You have like a 3x3 filter. It means you have 9 learnable parameters. We can use any filter. But the trick is that when we do convolution, we need to apply this filter 4 times. So in the initialization layer, you're gonna store the weights, right? And that is pretty similar to a normal convolution. You're gonna have output channels, input channels, kernel size times kernel size. That's what you're gonna do. But then when you're gonna implement your build filter like before, you need to build 4 copies of your filter in 4 different rotations. We're gonna do this by putting your filter in a larger tensor. You see that now it's not only output channels times, it's not anymore output channels, where is it? output channels times in channels, but it's going to be output channels times 4 times in channels times kernel size. Oh yeah, sorry, forgot to zoom in again. Is it better? A bit more? Okay, nice. So yeah, basically in this operation, in this method, we're gonna take your filter, which has not rotated, that's the learnable parameter, and you're just gonna paste it in 4 copies inside a bigger tensor, which has an additional dimension of size 4. And each of these dimensions, right? So the filter, the output filter, right at index I, this dimension of size 4, is going to contain the input filter rotated I times. Additionally, in this layer, you also need to implement the bias. The bias, right, is going to have like 1 parameter per output channel, but you cannot apply different biases on the 4 outputs of the same filter. Since if you rotate your image, you're going to also mix this, you're going to permit this channel. So it's a bit like in a normal convolution neural network, like you apply you have for each channel, you have a single bias then you use for all pixels. And the same concept is here. You have 1 unique bias that you use for all pixels and all rotations. So you just need to do this trick with the bias. The bias you store as a learnable parameter with only output channels, right, dimensions. But then you have to expand your bias by building 4 copies of the bias. That's going to be just let's see, oh yeah, before you had like only output channels, now you're going to build output channels times 4 bias by basically making 4 copies of your bias. The convolution operation then is pretty much like before. The trick is that conv2d does not allow you to use a filter which has this additional shape, output channels times 4 times in channels, kernel size. So what we do is a reshape. We merge together these 2 dimensions. So you now have 4 times more output channels, and the same you do it with the bias. You have 4 times more output channels. And now we can use our normal conv2d. The point is that we want the output also now to have this additional 4 channels. So once we have done our conv2d, we're going to reshape our output to have a batch size, output channels, the width and the height dimensions, but also 4 channels for the rotations. This part is taken care by me. What you need to implement is only anyways the bias and the filter construction. Is this making sense? Is it clear what's going on here? I want to hear an answer before going further. If you did not, understand something here, please like ask me so we make sure that this is clear. Okay, then I assume that you got this.
Yeah, I think it's
okay.
very
Then
let's go on.
Hmm?
Yeah, I think it's clear. So let's go on.
Okay, nice. So yeah, now we just check that this layer is equivariant, like we did before. I just feed a few random inputs. I check that the output is the same. That's the usual stuff. Okay, so now we have our group convolutional layer. How are we supposed to build the filter? Okay, that's precisely what you need to do here. And I think this is quite explicit. You have like, you can start with a filter, right? You build this filter with this shape, right? Now you can make it an empty filter, right? Torch.empty. And then you start filling in every entry I here for I from 0 to 4 with the rotated copy of the filter you built here, like in normal convolution. So as in a normal convolution neural network, here you would build self.weight equals some tensor of a shape output channels times input channels times kernel size times kernel size. And when you're here, you're just going to build a bigger filter, which contains the 4 rotated copies of this filter just stacked on top of each other, but along this dimension. Is that making sense? I don't want to give away the full solution. I want you to try a bit to implement it. But if you find difficulties on this part, we can maybe have a chat and try to figure out how to implement it. Yeah, now we have like our convolution layer, but we are not ready yet to build a deep neural network. And the reason is that the input space, right, was an image, and the output space was a function over a group of elements, right? So now we cannot put on top another of these convolutions because they expect a different input than what we have. To be able to build a deep network, we need to build a layer that gets in input the space y, the space of functions over group, over translation and rotations, and gives in output again y, so the space of functions on translations and rotations. Fortunately, like the group convolution, the definition of group convolution we had before, this is the same as before, is actually quite general. Like here in the previous case, we used P inside the Z2, so only P in the translations. But the same equation can be easily generalized by saying that X is not only a function over P, but it's also a function over the rotations. And the same is for the filter. Rather than using a filter which is only an image, we use a filter that is a function over the pixels and over the 4 rotations. Like you can go a bit through the details of how you reach this conclusion, but the final equation is pretty much the same. So you have the sum over all pixels like before, but now you have also the sum over all the rotations. Note that I use another variable here, s, and your input is not going to be a function anymore of only p, but also of s. Same is for your filter. The filter is going to be not a function only of p, but also of s. Then this rotation is as we did before. Also here we had this. And now let's just try to expand this definition as we did earlier. And you just have that, I mean, this is what we do here. You use this product and you obtain this new filter, which is nothing more than the filter psi, right? Rotated by r and then translated around with t. So again, this is nothing more than taking your filter psi, you rotate it by r for every possible rotation, and then you try to do convolution, you move it around over all possible translations. Not that the filter, however, is now parameterized also, is also evaluated at s, right? So just and then we sum over s. You should take this into account. But the rest, right, is your usual conv2d, like for a specific value of s and r, this equation here is your usual conv2d. We can see this maybe in an image. If these are your 4 inputs, now your input is not anymore an image, but again are 4 images, right? One for each rotation s, right, as we had here. Your output is also going to be a function over all pixels, but you have 4 channels, like 4 images, 1 per each rotation r. Now your filter is going to be not only anymore a single image like this one, but it's going to be 4 images, right? 1 for each s. You have a filter for s equals 0, for 1, 2, and 3. And now the convolution for r equals 0 is going to be the sum over all of these guys, right? This filter is doing convolution over this image. This filter is doing convolution over this image. This filter is doing convolution over this image. And this filter is doing convolution over this image. And then you sum all of them together and get this image in output. Now to get the output for other rotations r, you need to rotate your filter. And as happened before, right, when we rotate the filter, we first rotate each image, right? So look at this one as kind of an horizontal direction. We now rotate it and it becomes a vertical direction, but also we permute the 4 channels. So now this filter is not going to go here, but it's going to be here. And the green one is going to go here. Not that every time they are rotating by 19 degrees, but now it goes here. And all of these, right, that you see there, like each each of these filters is going to run a normal conv2d with one of the input images, and it's going to give us one of the output images. So you can imagine this as a 16, so 4 times 4 independent conv2d that you perform. In practice, like this 16 by 16 grids, like you can filters, you can stack them in your bigger filter, like in a conv2d, where you have like 4 input channels and 4 output channels. So that's what I'm trying to visualize here. Is that making sense for you? The trick again is literally what we had before, right? But rather than having a filter which is a function only over the pixels, so then rather than having a filter that is only an image, we have basically 4 filters, and you see that as a filter over as a function over the pixels and over the 4 rotations.
Hello. Please, I have a question about that one. So you say that you sum over the channel. So, and every time you permit the channel. So for instance, if you have a huge number of channels, are you going to consider all the permutation?
Yeah, I mean, you need to consider not all possible permutations of the 4 channels, but only the 4 permutations that are given by your group. Right? So your group has size 4, right? You are going to do only 4 permutations. Is this what you mean?
So imagine. So imagine that the cardinal of yours the set of your group is huge. So if you have a huge cardinal of the set of your group, and you have a huge number of permutations, so how do you deal in that case? Because that is an event that can happen.
Yeah. I mean, that is a literal. I mean, you have to do that. So that is actually a problem when you work with, for example, other groups. So if you don't have rotations are simple because you have only 4 elements. That's not that bad. You have only 4 permutations that you need to use, right? So it's still efficiently implemented as I'm showing you now. You just need to do convolution 4 times. But if you have as a group, for example, the group of permutations of a set, right, of n elements, the number of transformations you can do is n factorial, which is pretty bad in practice, right? So that is why, I don't know, for example, models like deep sets, right, don't use a group convolution on the group of all possible permutations. Otherwise, you would have a neural network which is huge. Like if you have to be equivariant to permutation of 5 elements, you already have I don't know what is 5 factorial, but probably a lot. Number of channels.
So you mean you have to choose a group which have a small number of elements. So that's what you mean? Yeah,
I mean, it depends on your problem, right? Like in this case, we are considering a problem where our group has a small number of elements. So we can do this approach and it works. When your problem has a large number of group elements, this approach becomes unfeasible. So for example, deep sets does not do group convolution. Like you cannot do that at all. So what deep set does is actually very similar to the isotropic filters we had at the beginning, where you have just one single filter, right, which is invariant to all the rotations. So you cannot use a filter like as here, which is any possible filter, but you use a filter which is already invariant. That makes your model less expressive, so it's not able to approximate any function, but at least it requires a finite amount of memory and you can actually run it. It's a bit of a trade-off between how powerful you want your model to be and how expensive you want your model to be. Is this making sense for you?
Yes, makes sense. So now about the isotropy of a filter. So in this case, the isotropy of the filter is just related to the fact that it's invariant to the rotation, or there's another way to consider that one.
Yeah, it's in this case, it's like the filter is isotropic, right? Because we are considering rotation. So I'm making sure that the filter, right, if you rotate it, looks like the same filter as before. So if you now imagine actually that you use that filter inside these equations, right? What you have is that, suppose that you take an isotropic filter and you do group convolution as we are doing here now. What happens is that you see that all these 4 filters would be the same filter, because if you use a filter that is rotation invariant, or maybe actually we see it better here. So suppose that instead of this filter here, you use an isotropic filter. Now what happens is that you don't need to apply convolution 4 times, right? That is expensive. Instead of 4 times, you had to do it hundreds of times. But you can do it only once, because anyways, these guys always give you the same result. And if, I don't know, say instead of rotation equivariance, you have a scale equivariance, you should have like something that is a infinitely wide filter, but that is a constant over the radius, for example. Is this making sense for you?
Yes, it makes sense for me. So thank you.
Okay.
So we were asking,
welcome.
since
Yeah.
we are almost at the end of the time. So do you want to continue? Because do you want to continue?
I think that we are almost done now. I think that this is really the complex part that took a while to explain. But if you got this part, what is left for you to do is only implementing it. So again, you have to you have like a group conv2d, right? And again, you have to implement your weights, the learnable weights. You have to then build a filter. That's pretty similar to how you did it before. So I think that if you did it in the previous exercise, you will be able to do it here as well. And then we're just going to check that your model is actually equivariant. And finally, we can build our neural network. I think that I can finish this. It's like really 2 minutes left. Is it okay?
Yeah, okay, yeah, let's continue then.
Yeah, once you have built these, right, those are all the building blocks we needed to build our neural network. So we are finally arrived to the point where we can stack our convolutions and build the final neural network. Before, like, yeah, there's a small theoretical question. You can have a look yourself on this. And then we can build our neural network. I just give you here like a description of how many layers, how many channels, and how to implement it. And then you just need to do this yourself. You can implement, you need to use the layers you have built before to generate this neural network. And then we just write, we check that the whole neural network, not only each layer, but the whole neural network from the beginning to the end is invariant to rotations. But we're going to put it in the end an invariant classifier because we want to train this network on MNIST. So then you just download the dataset from MNIST. I prepare for you like the data loader, the training loop, and the testing loop. And now we just build your neural network, we train your neural network, and then we test your neural network and check the performance. With the default parameters I give you, if you follow my template and everything, you should reach an accuracy of 93, 94%. I'm training these models very little, like it should take literally like 2 minutes to train a model and test it, maybe 3. Remember to set the GPU on Colab, not the CPU, but this should give you already like a good accuracy. But I mostly set these parameters randomly, so you can then manually change parameters, try to train the model for longer, change the batch size, make your model maybe a bit deeper, and try to get better results. So yeah, feel free to try that. But then we want to verify that the model is still equivariant after training. So make sure that if you change the model is still equivariant. You should reach at least this accuracy, so to get like all points in this exercise. For comparison, we then do implement an equivalent neural network, which instead uses the isotropic convolution you implemented before. The exercise is pretty much the same as before. It's just that you use the other layer, the isotropic convolution layer. And then we test the model, we train the model, and on this model, the idea is, showing you that why these models are less powerful. you will see that this model is able to reach only 45 to 50% of accuracy with the default parameters. You can try yourself to improve the model. If you make it bigger, wider, deeper, of course, it achieves much better results. But just as a fair comparison, here you have the same architecture, the same training loop, but you can improve over this. The last exercise. Oh yeah, here I want you to comment a bit on the difference between these results. Why do you think one model is better than the other? And then the final result is implementing batch normalization. This is a bit more complex result because I don't really guide you through this exercise much. I'm just asking you to do that. And I hope that once you arrive at the point that you have implemented the previous network, you understood what you need to implement batch normalization. In practice, implementing it is very easy. It's much easier than implementing convolution. It's really a line of code, basically. But I want you to explain me a bit what's the reason why you do that, what's the concept behind it. So I want you to write me something here. And then you just implemented the same neural network as you did before, but you also add batch normalization before ReLU. That's is usually done. And you should get an accuracy of around 95. So this is going to improve a bit your model. And that's all of the exercise. So this is the end of the homework. One last thing, and then we are done, is that you have this additional bonus question, which asks you to implement the rotation equivariant model, but this time you also use the reflections. At the beginning, remember, we built a group of rotations and reflections. And here, on your own, you should try to build a network that is equivariant to them. Yeah, that's, again, that is a bit more complicated. So keep this for the very last, if you have time for it. If you want to try, you can also get partial points here. So if you make an attempt and it looks quite nice, interesting, you can still get 5 or 10 points, but don't waste time on this if the rest is not finished. That is the end of my my introduction to the homework. Yeah, if you guys have questions, if you think you have some doubts, you feel stuck, we have a chat, right? So you can, of course, drop me a message and we can discuss and try to get through this. So yeah, that's it. Let me know how that goes. And otherwise, I wish you good luck.
Thank you very much, Gabriele. So before we end, does anyone have a question? Any pressing question? Okay. Okay, thank you very much, Gabriele, for your time. And
Sure.
I'm sure if you are going to listen from you again. I think today is the last day you are speaking to us.
Yeah. But again, if you have any doubts or you want to have a chat, feel free to drop me a message. I will be happy to have a chat.
Yes, yeah. So thank you very much for your contribution. Yeah.
Sorry, I was going to ask if Gabriele would be available to attend to some of our questions on CampusWare.
Yeah, I'm not looking at CampusWare now, but let me. Have you asked already some question there? Should I check?
I mean, not immediately, but of course, as we go through this, we'll probably have questions.
Yeah. I would be still online next week. So if you feel like you get stuck, as I said, feel free to drop me a message on CampusWare, and I will be able to reply. I don't know if you already have it, but I would recommend maybe drop a message on the general chat, right? So if some other student has the same doubts, that an answer can be helpful for them as well. If the question gets a bit too deep in the solutions, maybe we move it to a private chat to not give the solution to everyone. But yeah.
All right, thank you.
Yeah, so I can also keep an eye on the chat. If there is any person, I can send an email so you address it.
Of course. Yeah, that sounds good to me. Okay.
Okay, so thank you very much, and talk to you again.
Thank you. Of course. Have a good day.
You too. Bye.
Bye-bye.